In this video, I'm going to introduce you to a website called SwiftCalcs.com. SwiftCalcs is a free-form engineering spreadsheet which understands unit conversions. It is a really excellent tool. Free-form means pretty much that it does not have cells like Excel or Google Sheets would have. You create variables and you're in an environment that looks much more like a document writer than you do something that looks like a spreadsheet. Also, the other cool thing about this spreadsheet is that when you type in your equations, they actually look like equations that would be in a textbook. So you are documenting the equations as you're doing the calculations, which is really important in an engineering application. So to be able to log in, I'm already logged into my Gmail account, and when you click into the sign in, you can use your Google account to be able to go and create a SwiftCalcs account. So here it is. I've opened this up, and I can give you kind of an idea of how this works. Across are the typical things. File allows you to create a new worksheet. You can also click on the plus button down here. Projects are a way of collecting them. Edit is basically copy, paste, those kind of things. Options, defaults, inserting things. We're going to not get into too much of that. And of course we have help that allows you to look at this and find out more about this program. So what I'm going to do is show you something really simple, and then we're going to create a cantilever deflection spreadsheet. I have one set up over here already. I'm going to copy and paste some of the text that I would do to make things a little quicker. But to be able to create a spreadsheet, okay, to open up an existing one, I'm going to click in here, and this is the spreadsheet. It consists of text areas, that's using this command here, text mode, where you can put in basically descriptions as you like. Then it has calculation mode or math mode areas. That's this. These values are all over here where I'm defining variables. Here's a text region, here's a math region, text region, math region, text region, math region, and so on and so forth to be able to do this. So I'm going to go through the process of doing explaining how you do this rather than typing in all this stuff. I'm just going to copy it. Okay, if I click on the spreadsheet again, I can close it out. To create a new one, you simply click on the plus spreadsheet, give it a new name. I'm going to call this cantilever demo. Okay, and that basically has saved it. Now in text mode, all I have to do is click on this, and I will now do a Control-V paste, where I can type in a description of what I've done here. Okay, as going from that, I'm going to do this. It understands bold, italics, underlining, all that kind of stuff. You would type in typically the name of your spreadsheet, your name, dates, what the purpose is. In this, I'm going to basically implement the equation for the deflection of a cantilever beam. We've seen that in using Autodesk Inventor finite element analysis. We're now going to do the calculation by hand because it's a simple shape. A really cool resource that I like using and having my students use is called the Engineering Toolbox, and they have a section on cantilever beams where you can look up the displacement formula for that as well. In your spreadsheet, it's always a good idea to be able to document the variables you use, such as F will be the force in pounds force, A, the length of the beam in inches, E, the modulus of elasticity in pounds per square inch, and I is the area moment of inertia in inches to the fourth. And incidentally, while you're in here, okay, as you have text, okay, you can go ahead and use commands like this to be able to superscript or whatnot as you're working in here. I actually copied and pasted the formula from the engineering toolbox and pasted it in here. And then we start off by saying, you know, enter your input data, which is basically everything that you need to be able to go from there. I'm going to add some more formulas over here. B is going to be the width of the beam in inches, and H will be the height of the beam in inches. Okay, so we had a couple of variables that we hadn't finished on. Now I'm going to click to math mode, and now I can actually type in my formulas, or my variables. So I type in F and press equals, and that's going to allow me to indicate what we're using. Well, we had 100 pounds force, but up here I want to be able to go and insert my units. That's this area right here, the unit picker, and we're talking about force. So I come down to force, and I can say pounds force. Okay, so 100 pounds force, LBF. I press enter. For A, that's going to be length in inches, so I type in A. Incidentally, capitalization does matter, so in uppercase A, lowercase a, two different things. We know that we were going 6, and I'm going to use the double quote. It allows me to get into the unit field, and I can now just type in FT, and it's going to show me what's available as we go from there. So here's the cool thing. We're actually putting units into our numbers. So when it does the calculation, it will do all appropriate unit conversions as needed. Our modulus of elasticity, E equals, and if we go back to Autodesk Inventor, I think we were 1.27. Actually, let me fold it down here because I had looked that up before. 1.35 times 10 to the 6th is what we are using. So I'm closing that out. I'll get back here. Okay. 1.36 times 10. I'm using the up caret to be able to go and get that. I use a right arrow that selects the entire thing. And now, double quote, I can type in my PSI for pressure. Okay, that's the appropriate units that we're working for with that as we go from there. B, the width of our beam was 1.5 inches. The height of our beam was 3.5 inches. Okay, and basically that's everything that we have for this. We'll need to calculate the area moment of inertia to be able to do this. Perform this calculation. So I'm going to go to text mode and indicate calculate the area moment of inertia I. Okay, so let's go to math mode again, and here we go I equals B times H. Now I'm going to select B and H and do the division, the slash, and notice we get a long division bar. Okay, that's over 12. My H should have been cubed, so I can click back up there, do a caret, shift 6, and put BH cubed. Okay, so notice when we raise to a power, rather than seeing the caret, it actually puts it up here. We have something that looks very much like, okay, an actual formula. You print that out and anybody would understand. You'll notice by all of these that there's these little arrows. If I click on this arrow, it will show me the computed value, and by default I'm in meters, and it's meters to the 4th. If I wanted to change the units, I can click on this, and I can say I want inches to the 4th, press enter, and now I'm displaying in inches to the 4th. So any units I want at any time, I can switch things up. Incidentally, if you don't do appropriate units, you'll see some very funky results will happening. So this is one of the things that when students do calculations, they'll hate it at first, but the truth of the matter is, if they're not doing things correctly, it shows up immediately when you do initial calculations. So it actually turns out to be a really good thing. Utilizing these built-in units actually will allow you to deal with the physics of a problem and throw away all the conversions. Anyway, with that said, let's continue on. Our next thing is going to go text mode, where we're going to do the deflection. So I'm going to say calculate the deflection. Using the formula above. Go to math mode, and now to demonstrate using a Greek letter, here we have the Greek letter, and come down to whatever we choose to use. And for example, here's our delta. Our delta equals our force, our lowercase a, raised to the 3rd power. I'm going to select these two, all of this, division bar, 3 times E times I. Press enter. Okay, and click on the arrow, and we can see our deflection here is in meters. I'm going to just change that to inches and press enter. 1.707 inches. Okay, if we go back to our Autodesk, okay, when we were doing our analysis, okay, let's check our von Mises. We have 1.72. Let's look at our materials, make sure I got my units corrected here. Okay, here this is physical. Our Young's modulus is 1.36. Okay, 1.36 is the value I should be utilizing here. So let's take a look. 1.36 is the number that we are utilizing. So 1.72 versus the 1.70. Okay, so there is a little bit of variation between the two of these. Okay, our numbers are really close as we're working into it, but the answers can be off slightly. The really cool thing about this is if for some reason I wanted to change my units and say, oh, it wasn't 100 pounds, it was 100 newtons, doing this by hand, that could be a real problem. Okay, type in capital N, okay, press enter. I now have, my answer has been modified for changing 100 newtons. So I can do this at any point, change whatever my inputs are. LBF, pounds force, click out here, okay, and my answer is back. So switching units allows everything to take place as it goes in here. Everything, incidentally, is automatically being saved, so all changes have been saved. It's just like a Google document. That concludes this video on utilizing SwiftCalcs.